of those few people here in Europe that has actually quite an extensive experience on bills of materials and software bill of materials. And so I think from already the first moment you had spotted that the automotive industry is something which is slightly more mature than any other. I can imagine why that is, but I'm very anxious to hear from you how that happened. Because from my world where I'm coming from, I know that the automotive industry is extremely slow. Of course, very innovative, but those innovations only take place after sometimes even a decade when people started considering them. So I'm very much wondering how that meets then with the concept of bills of materials, software bill of materials in this particular case.
Sure, thanks. So indeed, SBOM is not a term that is strange to Cebellom. We have been dealing with SBOM for many years by now, and we help customers with creating SBOM, among other things that we do. So that's part of what we do at Cebellom. Let me just share my screen for a second. So thanks for the introduction, Ulrich. I came to speak today with you guys a little bit about our experience with SBOMs, some experience we have with customers of Cybellum. But I'd like to actually start with a story. So a few months ago, one of the manufacturers came to us to talk about the Ripple 20 vulnerabilities that came to life, were disclosed in the public. And this OEM was telling us the story of what happened when these vulnerabilities came out and what happened internally as they were investigating these vulnerabilities. For those not familiar with Ripple 20, this is a set of vulnerabilities that were discovered in some commercial TCP/IP stack that happens to be used in many industries, in many kinds of IoT devices, in the medical, automotive, and many other domains. So this was a very widespread disclosure that, of course, took the entire industry on its legs to investigate if it impacts them, many manufacturers. So they were telling us that when they received this new vulnerability, they start to perform an internal analysis of the potential impact on their components. And of course, the first thing they did is to identify which suppliers of components are relevant for this set of vulnerabilities, which components are containing this TCP/IP stack, and which suppliers provided them components with this TCP/IP stack. And this was not a small effort on their side. Once they figured this out, they start to escalate that to suppliers. We had a chance to glimpse at one of those internal emails and how they escalate to the suppliers. They basically gave them an SLA. They told them, you have to answer us by X amount of days, just a few days. Tell us if this is relevant for our product. And of course, it took much longer than the SLA. Took at least an extra week or than the original SLA. And the response back from the suppliers were, well, it depends on configuration items, depends on how you compile the TCP/IP stack, and so on. So this, of course, was much more complex than a yes or no. Then they worked on issuing a fix, and this is not the end of the story, because now they had to map which components on their side are actually in the field, in vehicle ID numbers, in actual vehicles. So they had to look at their database of sold vehicles, try to map the actual components and the versions to which vehicles and models are in the field are relevant for the vulnerability, and then release a software update to finally fix the issue. It took more than 3 weeks. So there are many hurdles in real life of vulnerability management across a supply chain. And we get to help our customers in these challenges. So how do you secure the unknown? Basically, what we see in the automotive space, you know, all of us had vehicles, I assume for many years, and in vehicles of the past, and I would say maybe older than 5 years or so, there were just a few electronic control units, ECUs, which are the computers inside the car, and there are many of those today, but in the past there were not so many. Their functionality was simple and there was no connectivity or very minimal connectivity. And today in any modern vehicle, it does not have to be an electric car, it does not have to be an autonomous car. In any modern vehicle, you have tens of ECUs. Almost everything is electronic, from the wiper controller to the engine controller, and obviously the infotainment system, telematics, ADAS systems. There are many bigger ones, which are real large computers today. They have a lot of functionality, a lot of interfaces. They're interconnected to each other and to the external world in many different interfaces. Some are more unique to the automotive industry, like CAN or CAN FD. Some are ubiquitous, like Bluetooth and Wi-Fi. It's much more complex than it used to be. But on the other hand, where in the past there was no relevant regulation, the efforts that the OEMs were investing in cybersecurity in the early days, and I'm talking again more than 5 years ago, were very basic, very manual, early days style. And there was almost nothing to deal with that related to post-production. So after the component went out, it was pretty much the end of the game. Nobody cared about it anymore, which is mostly the case with regular safety of cars, which has a standard, an ISO standard for many years. But when the components are tested and validated for that standard, pretty much, except recalls, things are stable, and there's no real need to have any maintenance post-production. But unfortunately, software is not the same, and cybersecurity of software is not the same. So today in the market, there are regulations. The WP29 that came from the UN is enforcing vendors to really do security across the organization, to have documentation of their processes, to have information sharing, to perform development with security in mind, document all of the results, test for security, and also continuously monitor security as components are produced and vehicles are produced. And today the expectation is of the regulation and the ISO standard, that ISO 21434, that followed the safety standard in a way, but focusing just on cybersecurity for automotive industry. Expect vendors to move at the speed of software. So if you release a new revision for an ECU, a new software version, and of course many may be released over a year, they all have to be evaluated because they represent potentially new risks. So that's a big challenge for an industry where there is a big use of supply chain. So if you look at SBOM analysis of a company like an OEM, or maybe even a supplier that is using other tier 2 suppliers, to perform SBOM analysis of a closed firmware component, a firmware that you don't get any details about. You don't have any paper that comes with it that tells you what's inside. Requires, first of all, to perform firmware analysis. And that's not a simple thing to do. So imagine you get a file that is a flash dump of that device, of that complex Linux-based or Android-based infotainment system of a vehicle or an engine controller or what have you. And some of the customers, at least in the early days, were pretty much trying to do it on their own. But there are many, many challenges in doing so, because when you get such a firmware, typically you don't have prior knowledge of the firmware. It's quite amazing to see, but even inside vendors, even inside suppliers, because of different political or legal implications, the product security teams don't easily get access to firmware, and nevertheless to SBOMs, which are potentially available in the development teams at least. So the bottom line is you end up getting binary files that you don't have any knowledge of the insides. And typically when you get such a firmware, you don't have any idea what's the file format or file formats in use, the file systems in use, the architecture of the component, operating system details, and of course, all the applications and software components and their configurations, which is what you will need to end up with vulnerability analysis. These are the basics for the cybersecurity research that you will have to do later on. There are existing solutions, but none of them are perfect. There are open source utilities by the tens and the hundreds. Each one is helping with specific parts of this analysis or firmware extraction parts, but it's a complex arrangement of tools that you'll have to gather to get a project going on. And commercial software also has issues. At least in the automotive industry, I can say that the world does not end with Intel and ARM like maybe the more general purpose IoT. There are many CPU architectures in use, many commercial operating systems in use, different file formats. Some of them are proprietary. And it's not something that is simple even for commercial software to support. And at least on the vulnerability side, vulnerability triaging based on the SBOM, based on the context information of the component, is also not something that is simple to achieve even with commercial tools. On the resources side, there's also lack of expertise. Firmware extraction is not something you learn in IT schools or anything like that. Vulnerability analysis and triaging also requires broad understanding of operating systems and their technologies. For anyone ever looking at a random CVE, you'll know what I mean. They can range across any mechanism in a system, and in order to understand them, you have to understand first that mechanism. Otherwise, it would be pretty much gibberish for you. So that's not a simple expertise. And for performing real analysis of binary code weaknesses and so on, that requires assembly level expertise, which is even more rare in the industry. It requires security research capabilities that are rare to find these days. So it's not so simple. Nevertheless, if you want to do that, basically what would be your methodology? You'd get these files. You'll have to perform using the different tools available to identify the file formats and extract the firmware. This requires some recursive hierarchical extraction of these file formats using different tools. You then use different methods of investigation to identify the OS and configuration. And there are different ways to identify SBOM components, looking for different signatures or hints inside the file structure for specific file names, specific strings, and so on, to identify what is the software that is used in the system, which software packages or components are installed in that system. basically the SBOM. Once you identify that list, the SBOM, you can identify if relevant the software licenses. There's an entire world of open source licensing that brings its own world of legal concerns and so on, and that is of interest on its own to manufacturers. And this would require some analysis of the SBOM to create the license list. And then it goes on to further security research of additional configuration items, security settings, and so on, and other issues that may pose a risk on the component. And this is using both the SBOM contents and also other configuration items of the component and the software that's inside to deduce those issues. And vulnerability analysis, I'm not focusing on that in this session, but this has a very close relationship with SBOM, because publicly disclosed vulnerabilities relate directly to SBOM entries. So an accurate SBOM would end up with accurate list of vulnerabilities, or relevant vulnerabilities. And inaccurate SBOM with missing items, false negatives, and incorrect items, false positives, would end up with erroneous vulnerability analysis that would have either missed some vulnerabilities, which may be critical, or have vulnerabilities that are irrelevant because that component doesn't really exist or that version is incorrect and so on. So this is very important aspect. So SBOM is really a basis for publicly known vulnerability analysis. And that's important. It then goes on to identify which ones are really relevant and identify potential exploits and so on. So that's all good. But with today's pace and today's number of versions, the main question would be, what about automation? This process, this methodology needs to be performed literally tens of times a year for each component. And if you have tens of components in each car and you manufacture multiple models in a year, you're talking about hundreds or thousands of components that you'd have to analyze maybe every few weeks. So this pushes the industry as we see it when we talk to customers in the last, I would say, 2 years. The big focus is on automation for scale. So even customers that have been doing these activities manually or partially manually using some tools, but human intensive, I would say, they are talking with us a lot about how can I automate? How can I do this faster? So Cybellum came up with a new approach called Cyber Digital Twins. We have been talking about Cyber Digital Twins in the last year and a half or two. What are Cyber Digital Twins? So these are digital replicas of device components that we basically create in our system as a representation or a virtual representation of the original components. And the purpose of these twins is to perform cybersecurity analysis that does not require the actual hardware itself or the original components. So basically, we gather all the information that is necessary for cybersecurity analysis, of course, for SBOM creation. We gather that and we store that as metadata in our system. We capture that, the essence of those products and the context information, everything that's important for cybersecurity research, and we put that in our database. And we create these entities called Cyber Digital Twins. And the beauty about Cyber Digital Twins is that they can be transferable across the supply chain. They can be used across the product lifespan, from development time when maybe you don't know so much, maybe there is no firmware yet, up to the ongoing operations of a product where the firmware is produced already, developed already, it's already in use in systems, and doesn't have to be cars, can be robotic arms like in the image here. and you still monitor the cyber digital twin over its life. Of course, with all the software revisions that come with this product. The cyber digital twin is following the original product lifecycle design, software lifecycle. So how do you develop with cyber digital twins in mind? So it starts on the upper left side in the design phase. An OEM has certain requirements. It plans to develop something. You can already create an SBOM from scratch using your initial thoughts about what would be the software inside that component. And you can investigate security implications of specific choices of software already upfront using the cyber digital twin, where you don't even have a real development yet. So the cyber digital twins can help already in the early design phase. You then go to development on the lower left side, and now you start having actual development, typically coming from suppliers, tier 1, tier 2. You actually already have firmwares, you already have things like cryptography keys and so on. And you can already analyze the cyber digital twins in our platform and already start getting SBOM from the firmware, getting analysis, getting security information already analyzed automatically from the system. And of course, there's a whole notion of development lifecycle. There's dev test cycles going on all the time. How do you manage vulnerabilities and so on? This is out of scope for our call today, but there's a whole notion here of a workflow that you have to go through to go from one version of a product to another, and how is it represented in the system. I'm not covering that right now. Once development is done, you then go to validation, and you want to validate maybe against specific acceptance criteria or specific policies that you may have. For example, one of the challenges that we see in the market is you have these large suppliers, and they already have security efforts across their development teams, but there's a big effort on standardization. So imagine a large development house. They have hundreds of developers across maybe 30 projects. And you have security appointed personnel across the projects, but each one has a little bit different way of looking at security. Each one has a little bit different criteria. And obviously, these projects are also different from each other, and they have the original requestors of those projects are the end customers, the OEMs, the manufacturers. And they have different requirements across the projects, but maybe myself, the tier 1, the supplier, I have my own policies, the bare minimum security that I require from any of my components. So how do you manage that? How do you standardize that across projects? This is a big issue that cyber digital twins help to resolve, because they standardize the representation of information, of components that may be very different from each other. And of course, the next step afterwards on the upper right side is operation maintenance. How do you monitor those components when they go out? So our platform doesn't really get anything installed on the used car or anything like that. But if the manufacturer knows that specific component for a specific version exists in a specific product, maybe a car, MRI, or any other equipment like the ones we've seen before, it can be tracked on the cyber digital twin side, the representation of that component with exact SBOM of the component that's in use in production. You can track that over time and understand what new vulnerabilities are out there that may impact that production product, and let you basically deal with that right away. So let's say you have this great IoT device that's out there used by millions, and there's a new Linux kernel vulnerability. How do you know that right away? How do you know which models of your great IoT device are impacted potentially by that new kernel vulnerability. So that's monitoring over time capability that you can do if you have a cyber digital twin for that IoT device in our platform. So the greater vision of cyber digital twins is transparency. Harmonization is about standardizing across different architectures, different component types, and so on. Imagine that we deal with today the general IoT space, consumer IoT devices, energy control systems, medical systems, and vehicles, and all of their different components, from the very basic ones to the very complex ones. How do you view things in the same way? How do you look at SBOM in the same way? How do you apply policies across components, across operating systems in the same way? That's harmonization. Traceability. The regulations, the standards are all calling for traceability all around. How do you keep track of everything that's going on, the versions, the changes, decisions, reports, and so on? So there's increased elements of traceability in our platform, and also in our later on in our future vision. More and more traceability. Anything that is being analyzed is tracked, anything is logged for future reference. This is where the regulation and standards are going. I always give this example of what traceability means is 2 years from now, something happens in one of the devices and it ends up being related to a certain disclosed vulnerability, and somebody's going to ask, why did you let that vulnerability still let the product be released with this vulnerability unresolved? Somebody will have to be able to pull out that decision and the evidence for that decision, why it was taken. Maybe it was still a good decision at the time it was taken. That's traceability, and that's a long route towards full traceability. And also collaboration. Cyber digital twins, today there's no true electronic collaboration between suppliers and customers, at least based on our experience. That's the case in the automotive industry, but also in other industries as well, the medical as well. It's not simple to transfer my original software to somebody else who needs to investigate it, or maybe needs my SBOM. There's even internally in companies, this is a big no today to send software between parties. And cyber digital twins provide an alternative way to send software between parties without sending the actual software. You can send a representation, a concise version of all the important details of that software. Because if you think about it, when I need to send some security information to somebody else, I don't really need the entire software. I only need the SBOM, the configuration, and so on, not the actual binary code or the source code, of course. So that's different use cases that we have today, and we are building upon extensions in the future. So how does it look in real life? On the left side, you first have to generate those twins, and you generate them either by, on the lower left side, sorry, manually. You can upload the actual files. You have to have software or firmware in binary format across the different architectures and different file formats supported. You upload that to the system, but on the upper left side, more and more customers are implementing this generation of representation automatically, right from their CI/CD workflows. So imagine a software build environment where you upload automatically and automatically assess firmware every maybe a week or so, and these builds are automatically assessed against certain policies and automatically take some actions back to the development teams, back to the security teams, maybe failing the build, maybe just reporting issues right back to the developers, maybe reporting it to product security. There can be different workflows here. But the notion that you catch things right when they are developed, which is a shift in the industry to do so. From our experience, at least in the automotive industry, customers are manufacturing tens of builds per year that they would like to evaluate. And typically they would have much fewer builds that they would really need to fully evaluate, maybe 2 or 3 releases a year. So there can be differences between the golden builds and the interim builds, but nevertheless, they would like to catch issues very early on to save trouble later. And again, there's a whole discussion here of how do you trace decisions and so on, and how does it impact, how do you fix those issues, how does it work with development teams. The platform, this is where it's all centralized. We support today flexible implementations from on-premises, entirely offline, up to public clouds. There are many different implications there. This is where it's all consolidated. It doesn't end with the system. There can be many integrations. Imagine the use case of SBOM when you take it, when you combine it with other systems, when you can escalate issues based on the notion of what software is inside, and maybe that sometimes it's not just about vulnerabilities. Maybe somebody added the software component that's not approved by your company. Maybe it's using some software license that has legal implications. So you want to escalate that to the external development teams, external, sometimes maybe internal in the company, but still external to you. You want to integrate with application lifecycle or product lifecycle management systems. We have a relationship, for example, a partnership with PTC, where a customer can use his PTC product lifecycle management solution and send as a testing module, sending products to test right from the PLM solution. OTA and firmware OTA updates, over-the-air update systems. You can combine security assessment to validate and have a stamp of secure go, no go before an update goes out as a last gate before something gets implemented in the field. And last but not least, this platform also enables product security incident response activities, where you can investigate vulnerabilities right in the system and see whether they impact your products. In fact, one of our most simplest features is a way to search for vulnerabilities and see which products you have in the system that have those vulnerabilities. And this used to take weeks to investigate. It takes mere seconds in a computer system. So it's very flexible and efficient in that regard. Once you have the cyber digital twins, you can assess them in different ways, perform all kinds of vulnerability and policy-based assessments, and continuously monitoring for new vulnerabilities. There are many details there. It's out of scope for us, but it's all starting with the cyber digital twin concept. So just some nice real-world insights that I thought would be interesting, maybe going back to some of the presentations earlier. Things that we get to see in real firmwares. First of all, there's more SBOM than meets the eye. I believe Jay was talking about nested components or deep inspection, or how deep is your SBOM, and detecting nested software components is something that we support and is very important. And here I'm just giving an example of the GDB debugger that's using zlib inside. And actually you have 2 distinct software components that are detected here. And it's very important to detect the 2 of them, because each one of them may have different vulnerabilities, different software licenses, and so on. So the implications are are important. It's very important to detect the two of them. And this seems to confuse quite a lot of people. We've seen cases where customers are just confused from the fact that you have more than one software component detected in the same file. Maybe it's not so intuitive that open source projects use other open source projects. That happens quite a lot. In some cases, it's easier to detect. In some cases, it's harder to identify. Some of them are more intuitive. Some of them are less intuitive. But nevertheless, it's very important to be aware of that. And another big challenge is commercial software. The world does not end in open source software. The issues are definitely not just in open source. You have commercial software, commercial operating systems. You have commercial software libraries that are used in firmwares. You may have first-party code that's commercial as well, and that's your own code. Getting to 100% accurate and complete SBOM is requiring many, it requires many aspects, to cover many aspects. Another thing is software component naming. Unfortunately, nobody, I guess it's the crazy jungle of the internet and open source. Moreover than that, you can see in the vulnerability databases that components change names over time. And since people are tagging packages, and since people are tagging vulnerabilities against package names, there's been many different names for projects in some cases. So for example, the PPP Linux component, which is quite common component, has different aliases in the NVD database. And it happens to be that the one that has the actual new latest vulnerabilities is not the intuitive one you'd think. It's actually the longest one, the third one on the list. So if you want to identify that you have the PPP package, it's not enough to just say PPP, because when you perform vulnerability analysis, you will have to map that to all those aliases in order to identify the real actual vulnerabilities of PPP package. So it's not so simple, and names do matter. Unfortunately, some projects, some open source projects rename themselves over the years. I definitely know that some tools, some solutions are using different names for the same package. So there's no standardization there either. So this whole concept of component names is also not a simple issue today. Other aspects that we get to see in actual firmware, which is kind of interesting, that SBOM can be a source of insights on its own. It's a list of components, but at the end of the day, that list may lead to interesting conclusions. For example, on the left side, unsafe software. So we typically deal with embedded software, devices that go inside larger products or some systems. Again, in the different industries we cater to. And you don't expect to have a printing software, for example, in a device, inside a car, or debugging support utilities that are left out from the development period, or troubleshooting utilities, which are gold mines for hackers, but nobody really needs them in a production environment. So these are little gems that can be identified just by reviewing SBOMs or using some policy-based mechanisms to review SBOMs. Aging software is also an interesting aspect. You don't expect modern products to still have software that's 19 years old when there is later, much later version updates that can be used, because these projects are maintained. Some projects are not maintained, and it's not simple, but some, definitely the majority of open source that's used today is maintained. Old is bad in software. In most cases, it means there are open vulnerabilities, and of course, it may be end of life in terms of the community support and so on. There are other aspects to this. And I think the average person would agree that difference between 1 or 2 years to 19 is very big, and should raise some eyebrows. And definitely we get to see that in firmwares all the time. So I'd like to just give a very brief demo, and then we can move on to a short talk about very short talk about Cebellum, and then just move on to Q&A. So this is the Cyber Digital Twin platform. You can see here that we have in the system here. This is a demo system, so these are kind of sample components that try to cover a wide range of devices, wide range of architectures, wide range of operating systems that we are playing here. You can look at these devices, and you can just look at what's inside a device, and you can see that we have a lot of details that we gather from the device, or we let the user manually put his information of the device to tag, for example, the vendor name for later on tracking the production phase and so on. Maybe interesting to start is the file structure. So this is the original file that was uploaded, right? That's a 19 megabyte file, and it was automatically extracted to get to all of its internals in order to perform the automated SBOM detection, right? This is the basics of the detection. Is first of all extracting all the files until the smallest parts are exposed.
Eyal, can I ask you, just for the sake of making sure that we understand each other correctly, if you say the digital twin, how digital is a digital twin, or how much twin is it? I mean, some people describe a digital twin basically as the description of whatever is inside. Is this, because Wim was also asking the question about it in the chat, is this a complete virtual virtual machine of a piece of software that you run, or how digital is digital?
Yeah, so let me start maybe by how twin is the CDT, how much twin it is. So it's not a virtual machine. It's not attempting to run the original component. The challenge, at least that we got to see when we started to develop that, is that there are so many different kinds of devices, and if you will try to emulate them, this will create a big challenge, and that's not what we do. So the term digital twin that we use may confuse some people to think that we are like the industrial, maybe digital twins, where you run the turbine, the virtual turbine, 24/7, try to see what are the implications of different things. So that's not what we do. We perform static and some dynamic analysis on the files that we get. So it's not entirely just on the files. We do identify some issues by running parts of a firmware, I would say, or parts of the code. But in essence, that's what lets us support in the same system. And our software runs on standard 64-bit Intel machines today, whether cloud-based or physical or what have you. But on that same software of us can identify and extract and find issues and SBOMs in ARM-based platforms, QNX, VxWorks, Windows, Linux, and also microcontroller based, which are very different CPU architectures like Renesas and Tricore. So you can see all of them analyzed in the same way. All of them would look similar to this, because we don't have this challenge of trying to run the QNX OS in the virtual machine or so. So it's not exactly like a full-blown digital twin. Maybe how digital they are, maybe I would read that as how much exposed is the software that's inside. we expose quite a lot. I will show some of it maybe in this demo. I mean, you can see obviously our focus here is SBOM. So obviously we identify software components. We identify a lot of details on the components that we gather, and we cross-match with different feeds of informations. You can see here, for example, a package I just chose randomly. This was detected based on some information we identified from, in this case, one of the files. We identified it as part of the IIoTSBOM software component. So there are many things like cryptography keys, sensitive information like URLs, shell history, and so on, network interfaces, IPs, MAC addresses, PII, email addresses, phones, and so on. Configuration items of Linux and web services and applications, so on. Is that extensive? Yes. Is that 100% of what you may find in the firmware? Obviously, our goal is to cover 100%. We are extending the platform on a constant basis to support additional items from the operating system, additional operating systems, additional configuration items. So it keeps extending. If you would look a year ago, we would have, less menu items here, less items in each category. This keeps extending all the time to be able to identify more security issues on the configuration side mostly. So yeah, it's a never-ending goal to cover everything, cover all of the operating system, all of the configuration items. But this is our a lot of work that we do constantly. So
yeah, that's for sure. I can see that. And also for clarification, maybe. So if I understand correctly, part of this repository is based upon the analysis that you do on this system, for instance, and partially also based, I guess, from what you receive from the device manufacturer, the machine manufacturer.
So maybe let me put some better order here. This is this is a manual way to upload software. To create it manually, you just give it a name, Loven1, and then you can give all kinds of information, and the next step would be to supply that from a URL or a file. You just upload a file, and that starts to be automatically scanned and assessed to create the digital twin. Part of that creation, and this is how these files were created. The ones you see here, they were created that way. Part of that, the first phase is the file extraction. Everything is extracted from the file. Again, there's no notion here, any additional information we supplied really from the manufacturer. It was just the file. We identify the architectures, we extract the file systems, everything is automated. And then there's a software composition analysis to create the SBOM. And then you can create different assessments here. There are examples of vulnerability assessments and so on that you can create. You can apply different policies on that component to identify security issues according to your requirements and so on, or maybe industry standard best practices or regulations. We do let you interact with some of the results to be able to edit stuff. So for example, if there is an additional software component that was not identified because it's some proprietary software or something that was not identified automatically, you can edit the SBOM, you can interact with it and make changes or additions and deletions and so on. So in regards to input, we do let you input your own information and interact with the results. That's the way I like to call it, in different ways. So I hope that answers that part. But the analysis itself is really, it's a black box type of arrangement. We don't expect you to have any a priori information on what you supply.
Got it. Thank you.
That's part of answering that whole supply chain challenge, basically, that you don't have that information. In fact, we talk today and we sell today to tier ones, to real suppliers of equipment, and it's teams that literally sit next to development teams. They work directly with them, and they don't have SBOMs. They don't have the full information on what's inside the build firmwares, even though they have full access to source code. Because it's not easy, even if you have source code, to understand the full SBOM. There are challenges there in identifying what is actually being built into the final firmware. You have to do a real full analysis of the build environment as well, of the build configuration and so on. So it's not a simple problem, even to ones that have source code itself.
Fascinating.
So yeah, we definitely live and breathe SBOM in the company. We deal quite a lot with SBOMs, so it's nice to see that the industry is now putting a lot of attention on this. That's what we've been doing for some time, and of course this is an entire basis for the other capabilities of the system, which is totally out of scope here, but there's a lot that we gain afterwards from the SBOMs, mainly in the area of vulnerability analysis, entire capabilities that are built on top of the SBOM. Because SBOM may be relevant for again, licensing investigation. Yeah, that's one part, one aspect, but the common aspect would be vulnerability analysis, which is what you will have to do next with your SBOM to identify how are you impacted by this SBOM. The nice thing about digital twins is that you can imagine you can create such a digital twin without having any firmware whatsoever, as I was showing on one of the earlier slides, and you can basically change version numbers and see what the impact is on vulnerabilities, and maybe take a real firmware and say, oh, maybe I have some vulnerabilities. Maybe let's see what will happen if I will upgrade as a utils to a certain version, and you can see the implications right there. There are many cool things you can play when you have maybe I would say a virtual SBOM of a component. So I hope that gives you some notion of our system. We're always there to tell you more about it if you're interested. So
thank you very much.
Maybe let me just go back to the final slides.
Yes.
So just a few words about Cybellum. We help manufacturers of different kinds, different sizes, different industries to develop and maintain secure products, obviously mostly connected products. We focused many years on the automotive industry, but we do play in the medical and industrial industries as well. Our extensive coverage for operating systems and device types and CPU architectures have allowed us to really cater to those industries. Just as one example, we have extensive support for Windows, which is not used in automotive except on the server side, not inside vehicles, but is very widely used in medical. We have extensive support and software exposure capabilities for Windows, just as one example. We're a global company. We are active in many standards and alliances. In fact, we do have a relationship with the NTIA organization for a few years already. So we are aware of the SBOM efforts and the different file formats and so on. We can export to SPDX and Cyclone DX, which were mentioned earlier. We sold till today to very large companies on the automotive space and other areas like defense and energy and so on. Many names cannot be listed here. Cybersecurity is an anonymous type of field where companies don't want to be publicly announced that they use a certain solution. received many awards and so on. So that's just a little bit about us. And we provide solutions, and you've seen it very briefly, that is powered by the Cyber Digital Twin technology, mostly around vulnerability management, from design till operations, compliance with different security policies and standards in an automated way, and to continuously monitor and provide incident response for products. So all around product security, from assessment to operations, if I have to summarize. So we put out some link for additional content. You can obviously see quite a lot on our website to learn more about what we do. And we can open it up for questions or additional questions.
Great. As I said already, thank you very much. It was a very in-depth and an interesting overview. I already raised the part of the question that we mentioned in terms of the virtualization. He also wrote SAST and DAST testing. So yeah, I think that's also probably the perspective that you're bringing here. So from the perspective that we are sitting here now in trying to get production companies that are producing machines and different types of devices to get to be more transparent, to open up on their components. I think it's definitely obvious that you can help them in just already discovering what's potential vulnerabilities that they have, that they probably didn't even know that they had. So that's pretty clear. Also from an end user perspective, it does make a lot of sense. So what do you see basically as your further sweet spot in developing? Is it the end user companies, or is it more the production manufacturing companies that you would aim for?
We are typically aiming for product security teams at manufacturing companies, companies that are either manufacturing components themselves, so they are suppliers, if you may, and also to customers who are building the larger systems. They are very interested today because they are typically liable for the regulation, liable for because of standards, because of their own policies. I think as was mentioned earlier, when you manufacture a product, you are the one that need to care about all of the security implications. So to both of these, typically not the end real user, not the driver of a car, right, but the manufacturer of the larger system, and the first level suppliers. These are the main ones interested.
Got it.
Such a solution.
Yeah. So there was also the relationship I think mentioned with LG. How is that sustaining, or how do you use that one?
Yeah, this is a very recent announcement that LG Electronics, one of the largest electronics manufacturer in the world, and definitely one of South Korea's largest companies, have invested in Cebellom, and this will end up as a full acquisition of Cebellom. Nevertheless, we are staying as an independent company because LG realizes that the market of product security is complex, so we are not going to be an LG only type of company or anything like that. We are continuing our standard operations. We sell to different markets, not just to automotive or the markets where LG Electronics is playing. The part that LG is mostly interested in us is the vehicle solutions part of LG Electronics, called LGVS. So we are staying as an independent company, and we are still actively selling into the other markets that we are active at, and obviously not just dealing with LG. So
got it. Yeah,
that's obviously strengthening our position in the market as a viable solution. We are now still an independent and very dynamic company, but nevertheless owned by a very large conglomerate with big pockets. So a vendor that is there for years to come, and that strengthens our own existence for years to come as well.
And a vendor which can probably also use every once in a while your solution. For
Yes, yes. Only once in a while.
Okay. I don't see any questions popping up anymore from participants. So thank you very much. In any case, Eyal, again, to present. It's been a pretty extensive overview, so greatly appreciated. So I'd say let's stay in touch also over the next coming months while we are developing these activities. You're very welcome to join in also towards the future, and to also help us putting not only SBOMs, but I think also what you pointed out here, that I mean, SBOMs is again only one way to approach these different things, but it's really a part of a larger challenge that we are facing. And what I do like is your very much industrial approach, slightly also much more related towards devices even. Where we can definitely see that even on industrial devices, software is massively important. I think maybe at some other point in time, the challenge is going to be, what about bare metal devices, and how do we deal with those? Because that's yet another Pandora's box that might need to be opened. Exactly. But definitely in this case, I think it's very helpful and very insightful.
Thank you.
All right. So with this, I'd say thank you also for the participants for staying in, and thanks for the interesting questions and comments. And I'm looking forward to our next session, which we will be organizing in early February. So it will be the 2nd of February, and then probably for the next face-to-face, or the first face-to-face, not the next one, but the first face-to-face, somewhere mid-March. So in the meantime, I hope this Omicron stuff gets clarified as soon as possible, that we can get rid of COVID and Corona even